Hello guys, and welcome back to Introduction to Number Theory. This time we will discuss some cases related to factorization and especially uniqueness of the factorization in Euclidean rings. And I would like to talk about indecomposable elements, but first we should start from another notion. Let's discuss invertible elements. What does it mean to be invertible? Well, an element is invertible if it has another element such that their product is equal to 1. Let's just take a look. So we consider an almost arbitrary ring, but we need this ring to have a unit inside it, which is just an element such that any other element multiplied by this unit is still the element that we initially multiplied by this unit. And we can consider the set of all elements such that they are in some sense divisors of this unit. We denote this set as R with a small symbol like an X, but it is not an X, it is a sign of multiplication, because this set actually forms a multiplicative group. And all elements of this set are called to be invertible, are said to be invertible, and we will occasionally write D as C to the power of minus 1 or 1 over C. So now that we have invertible elements, we can go on and discuss indecomposable elements. So we say that element Z, element of the ring, is indecomposable if, and only if, this is a definition, there exist no such A and B, also elements of the ring, such that Z can be represented as a product of A and B, and at the same time both A and B are not invertible. So Z cannot be decomposed into product of two not invertible elements. In that case, we say that Z is indecomposable, or we can say it in other words. We can say that for any two elements A and B such that Z is equal to their product, one of these elements must be invertible, either A or B. And let me just remind you that this belonging to R multiplicative means that there exists 1 over A, an element which is inverted to A, and B being invertible means that we have element equal to 1 over B. And one more thing, last but not the least, Z is called indecomposable only if it is not invertible. So invertible elements are invertible. We do not have anything to do with them when we discuss indecomposable elements. Now let us consider several examples of indecomposable elements. For instance, just take our usual ring of integers, and we know that all prime numbers, which we know very well, are indecomposable. But here I would like you to pay attention that both plus and minus prime numbers are indecomposable. So plus or minus, it doesn't matter. Actually, these numbers act almost the same when it comes to division theory. Well, there are several representations of these numbers as a product of two other numbers, and in each of these representations, one of the factors is equal to 1 or minus 1. And these factors are actually invertible. Another example, we can consider the ring of polynomials in one variable over a field. Here we just take a usual field of real numbers. And let's consider polynomial, say, t plus 5. Will it be indecomposable? Suppose it is decomposable and can be represented as a product of two other polynomials. Well, let's just take a look at the degrees of these polynomials. Well, we understand that t plus 5 has degree equal to 1. So the sum of degrees of polynomials x and y should be also equal to 1. From this it follows that either x or y has degree equal to 0. Well, for a polynomial, a degree being equal to 0 actually means that this polynomial is invertible. Now we have third example. Let's consider a ring which we gain by adding I multiplied by square root of 5 to the ring of integers. Well, actually this is a set of all numbers, all complex numbers, that can be represented in the form a plus bi square root of 5, where a and b are arbitrary integer numbers. Well, this is also a ring. And in this ring, we can consider an element 1 plus I square root of 5. Well, I is of course an imaginary unit. Will this element be indecomposable? Well, let's try to represent it as a product of two other elements, x and y. And now just calculate the absolute value of this complex number. We know that it should be equal to the product of absolute values of x and y. And here on the slide you see squares of these absolute values, but nevertheless they should be equal. And we understand that the square of the absolute value of our number 1 plus I square root of 5 is equal to 6, because it is 1 to the power of 2 plus square root of 5 to the power of 2. 1 plus 5 equals 6, so this is the square of the absolute value of our element of this ring. And it should be equal to product of two obviously integer numbers. The square of the absolute value of x and the square of the absolute value of y. Well, now we understand that the absolute value of x, actually its square, is either 1, then x is invertible, or it is equal to 6, but then square of absolute value of y is equal to 1. So in these cases, either x or y is invertible, but could square of absolute value of x be equal to 2? Well, let's just take a look. If we have real part of x and imaginary part of x, then the square of its absolute value is real part to the power of 2 plus 5 times the imaginary part to the power of 2. Well, x2 is not actually the imaginary part of x. It is b from the definition of these numbers. So actually imaginary part of x is equal to x2 multiplied by square root of 5. Okay, so we need to find integer numbers x1 and x2 that satisfy this equation. And just taking a look at it, we understand that there exist no such integer numbers. So, okay, so square of absolute value of x cannot be equal to 2. But can it be equal to 3? Well, let's do the same thing as in the previous case and just write the equation where we need to find integer values of x1 and x2 such that x1 to the power of 2 plus 5 times x2 to the power of 2 is equal to 3. And we understand that there also exist non-such integers x1 and x2. Well, I believe that it means that our element 1 plus I square root of 5 is indecomposable in this ring. And as an exercise, I suggest you prove that also 1 minus I square root of 5 and also number 2 and also number 3 as elements of this ring are also indecomposable. Good luck.